A cosmic enigma defies odds and logic. China's Mars orbiter captures a rare glimpse of Three-Eye Atlas.
Astronomers are now watching an interstellar object break apart, and no one can fully explain why. Detected in July 2025, Three-Eye Atlas was expected to behave like a typical comet. Instead, it brightened rapidly, drifted off course, and began fragmenting far sooner than models predicted. Each new observation has only deepened the confusion. In this video, we'll go step by step through what changed, what's been confirmed, and what remains unexplained. If you'd like to follow how this story unfolds, consider subscribing and sharing your thoughts below. Let's start with how Three-Eye Atlas was first detected, and why its early data already hinted at something extraordinary. Soon after Three-Eye Atlas was confirmed as an interstellar visitor, the initial sense of routine observation began to fade. What began as a straightforward tracking campaign quickly turned into a puzzle. Within just a few weeks, the object's light curve stopped behaving predictably. Its brightness surged, then fluctuated in ways that standard thermal models couldn't reproduce. Every new dataset seemed to contradict the previous one. The early assumption was simple. Atlas was expected to act like a typical comet from another star system, slowly heating as it approached the sun and releasing gas in a steady, measurable pattern. But the recorded energy output didn't align with that model. It wasn't just brighter than predicted. It was too bright, and for reasons that didn't fit ordinary sublimation. Instruments designed to measure outgassing and dust density started producing conflicting results, forcing teams to recheck their calibrations. When the same anomalies appeared across multiple observatories, equipment error was ruled out. By late July, what had seemed like a minor discovery was being described in technical reports as inconsistent with standard cometary physics. The projected mass loss rates required far more surface area than the object appeared to have. And yet, the increase in luminosity was real, verified independently across ground-based and orbital telescopes. Researchers began to realize they were observing not a steady process, but an evolving event, something accelerating, fragmenting, and changing faster than any natural model predicted. The early confidence that this would be a routine analysis of a familiar phenomenon gave way to something else. Quiet recognition that Three-Eye Atlas was behaving unlike anything seen before. The next challenge was to explain how an object so small could produce such an enormous and unstable release of energy. Among the first interpretations proposed was that Three-Eye Atlas had fractured apart, a natural response to the stress of entering the inner solar system. Preliminary models described a catastrophic breakup, with solar radiation and tidal forces pulling the nucleus into countless fragments. Each new surface exposed to sunlight would release gas and dust, accounting for the object's sudden rise in brightness. It was a plausible, data-driven hypothesis, refined by multiple research teams, including one led by Avi Loeb. The initial projections suggested that if the object had truly disintegrated, its collective surface area could still explain the observed energy output. Yet, when detailed imaging and spectroscopy arrived, the behavior didn't align with what a chaotic debris field should look like. Fragmented comets typically produce uneven patterns, scattered plumes, fading hotspots, and irregular fluctuations in light intensity. Atlas, however, displayed a strange consistency. Its luminosity remained steady across days and even weeks of observation, as if the individual pieces were responding in unison. Spectral data deepened the puzzle. Despite the presumed fragmentation, the material composition stayed remarkably uniform. The same carbon dioxide and metallic signatures appeared repeatedly, even as the object continued to evolve. In a natural breakup, these readings should have grown increasingly disordered as fragments cooled or drifted apart. Instead, the spectra suggested coherence, a structure maintaining stability despite violent disruption. Astronomers began noting that the energy output wasn't decaying as expected. It was sustained, organized, and measurable with surprising precision. Rather than confirming a random explosion, the evidence hinted at a process with internal structure, something maintaining equilibrium where none should exist. The explosion label no longer captured what the data showed. Atlas hadn't simply fallen apart. It was behaving as if the fragments were connected by some shared, invisible order that standard physics couldn't yet account for. As the observations continued, a new inconsistency emerged, one that cut directly into the physics of what Three-Eye Atlas was supposed to be. When researchers calculated how much energy would be required to sustain its extreme rate of mass loss, the numbers didn't add up. Based on the intensity of its gas and dust emissions, the nucleus would need to measure at least 14 kilometers across to expose enough surface area for that level of activity. But when the Hubble Space Telescope imaged the object in July 2025, the data told a different story. The nucleus wasn't enormous. It was tiny, somewhere between 1 and 2 kilometers in diameter. Even the upper limit left a gap too large to reconcile. You can't hide 14 kilometers of rock from Hubble, one researcher commented, summarizing what became known as the mass loss paradox. To explain the discrepancy, scientists ran simulations of possible fragmentation scenarios. They considered whether thousands or even millions of smaller pieces might collectively match the required surface area. Yet even under generous assumptions, the numbers refused to balance. The total reflective area fell short of what was needed to release millions of tons of a material every second. The light curve also remained too stable for a debris cloud that large. It showed coordination, not chaos. In standard comet physics, energy in equals energy out. The sunlight hitting the surface determines how much gas can sublimate and escape. But in the case of 3I Atlas, the output exceeded the input by orders of magnitude. Something was fueling a reaction more powerful than solar heating alone could explain. If the nucleus wasn't large enough to drive this process, then what was? If not a massive comet, how did a small fragment from another star system shed mass at a rate that defied its own dimensions? As researchers worked to explain the mass loss paradox, another inconsistency appeared, this time in color. Throughout August, photometric data showed that 3I Atlas wasn't becoming redder as it approached the Sun, as nearly all comets do. Instead, its spectrum shifted towards shorter wavelengths, giving it a distinct blue tint. That transition was subtle at first, but as the object moved closer to perihelion, the effect grew unmistakable. Under normal conditions, solar heating releases dust and vapor that scatter sunlight toward the red end of the spectrum. The more material a comet emits, the warmer and redder it tends to look. Blue, on the other hand, implies reflection from cleaner or more metallic surfaces, something far less common in natural bodies. For a time, some suspected an observational error or contamination from nearby background stars. But independent measurements from multiple observatories confirmed the same result. 3I Atlas was genuinely shifting toward blue. The discovery deepened the mystery. A bluer signature could mean several things: metallic compounds, finely structured silicates, or even particles reflecting light in ways unfamiliar to standard comet models. None of those possibilities fit comfortably with what was already known about the object's volatile emissions. The data suggested a composition inconsistent with both Oumuamua's inert surface and Borisov's carbon-rich dust. To some researchers, the simplest explanation was that the surface material had been altered by intense heating, exposing subsurface layers rich in metal-bearing compounds. Others speculated that the fragments themselves might contain alloys or crystalline grains, formed in a different stellar environment. Whatever the cause, the result was clear. 3I Atlas was not following the photometric behavior of any known comet. Its color, once expected to reveal a familiar chemistry, instead signaled something foreign, a spectral fingerprint that didn't belong to the solar system at all. By early November, astronomers believed they had cataloged most of 3I Atlas's anomalies. Then came the images that changed everything. On November 9th, 2 independent observers working with the British Astronomical Association captured new high-resolution photographs that revealed the structure of the material streaming from the object. Instead of the diffuse, uneven plume typical of a disintegrating comet, Atlas displayed a series of narrow, sharply defined jets arranged in geometric order. Each jet appeared collimated, extending in precise directions that didn't correspond to the chaotic spin expected after fragmentation. The pattern wasn't random. Several plumes aligned at consistent angles, forming a symmetrical network that looked organized rather than explosive. Observers described the shape as structured coherence, a phrase rarely used to characterize natural outgassing. Under ordinary conditions, thermal jets erupt where sunlight hits a rotating nucleus unevenly, creating shifting plumes that change position from one day to the next. But in the November data, Atlas's outflows held their configuration over multiple observation sessions. The geometry was difficult to reconcile with natural models. Even advanced simulations of rotating comet fragments failed to reproduce the stability seen in those jets. The outflows didn't appear to be spreading freely into space. They seemed directed, as if channeled through invisible pathways. The overall symmetry suggested a level of control that pure sublimation could not maintain. One observer remarked that it looked as if something was steering the debris. When the images were compared to previous cometary breakups, none matched the precision or scale on display. Instead of a diffuse cloud dispersing with time, Atlas presented a dynamic but ordered system, radiating along well-defined axes that defied expectation. Whatever forces were shaping those jets, they hinted at mechanisms not yet understood. And that wasn't even the most surprising part. Soon after the organized jets were documented, another pattern emerged, one that would prove even harder to explain. When mission planners analyzed the trajectory data, they noticed that 3I Atlas wasn't simply moving along its projected path, it was accelerating. Not just slightly, but measurably and consistently, in a way that solar gravity alone could not account for. The calculations indicated a sustained acceleration of roughly 94 kilometers per day, squared at its closest approach to the Sun, a number that immediately drew attention across observatories. Natural comets sometimes show mild non-gravitational forces caused by uneven outgassing as solar heat vaporizes surface ices. These effects can alter a trajectory by small margins, centimeters per second per day, but never at the magnitude recorded for Atlas. The thrust implied by its changing position was too strong, and more importantly, too stable. It persisted even as the object moved away from the Sun, where solar heating should have diminished. Teams from NASA's Jet Propulsion Laboratory and several European observatories rechecked their orbital models, assuming at first that an error had slipped into the datasets. But the readings held. Radar tracking, optical astrometry, and even independent amateur measurements confirmed the same acceleration curve. There was no computational mistake. The object truly was gaining speed. The implications were difficult to accept. For Atlas to accelerate that quickly, it would need an internal process generating continuous thrust or reflecting momentum with extreme efficiency. Neither comets nor asteroids possess mechanisms like that. The data placed 3I Atlas in a category with no precedent. A body that appeared cometary in composition but behaved as though it were being propelled. What was once a routine observation of a distant traveler was now an open question in celestial mechanics, forcing scientists to reconsider what might be driving it. Faced with an acceleration that resisted every conventional explanation, a few researchers began outlining alternative possibilities. Among them was Harvard astrophysicist Avi Loeb, who proposed that if 3I Atlas's motion couldn't be fully explained by sublimation or gravity, then perhaps another form of propulsion was at work. The idea wasn't presented as a conclusion, but as a framework, one that invited testing through measurement rather than speculation. In Loeb's interpretation, the organized jets observed in November might not be random outgassing at all, but the result of directed emission, a process in which expelled material produces controlled thrust. If an object possessed built-in structures capable of channeling heat or gas in specific directions, it could, in theory, sustain acceleration far greater than a melting comet's natural output. This didn't imply intent or design outright, but it opened a legitimate scientific question. Could some interstellar bodies carry mechanisms, natural or otherwise, that behave like propulsion systems? The proposal was controversial, largely because it challenged traditional boundaries between astrophysics and engineering. Yet the reasoning behind it remained methodical. The energy balance calculations, jet geometry, and spectral uniformity all pointed toward processes that ordinary cometary physics couldn't easily replicate. Loeb emphasized that the answer would not come from theory alone, but from the data collected in the following months. Spectroscopy, trajectory tracking, and deep field imaging from Hubble and the James Webb Space Telescope. That data, he argued, would determine whether 3I Atlas could still fit within a purely natural framework, or if its motion required new physics to describe. The approach was cautious, not sensational. Rather than claiming proof of an artificial origin, it treated propulsion as a hypothesis, one to be tested, refined, and either confirmed or rejected by observation. In the end, only the measurements would decide which model survived. By late November, the effort to study 3I Atlas was nearing its end. Hubble and the James Webb Space Telescope were using their last observation windows before the object slipped beyond range. Its brightness was fading. Quickly, and by mid-December, it would be too dim for meaningful data collection. After that, only its trajectory, a silent line through deep space, would remain. Researchers called this the collapsing window. Every spectrum, every image, and every reading taken during these final weeks would become the permanent record of humanity's encounter with Atlas. There would be no second chance to re-observe it, no follow-up mission to confirm what was seen. Teams across observatories synchronized their instruments, hoping to capture any final details, temperature changes, dust dispersion, or spectral shifts that could confirm one theory over another. If the data revealed chaotic fading, fragmentation would likely explain it. But if the jets held their structure or acceleration continued as sunlight weakened, the mystery would deepen. By the end of December, 3I Atlas would disappear into the outer system, leaving behind a finite archive of numbers and images. Its behavior would be studied for years but never witnessed again. And so, the central question remained: had astronomers recorded an extreme case of natural physics? Or something that hinted at an origin far less ordinary? Whatever 3I Atlas proves to be, it's already reshaping what we know about interstellar visitors. Expected to act like a comet, it showed acceleration, color shifts, and structure that defied existing models. As final data are studied, what do you think these patterns mean? Share your thoughts below, and if you enjoy exploring the unexplained side of science, make sure to subscribe. Thank you for watching, and I'll see you in the next video.